Yeah, so far actually what we have discussed, we have described this stochastic process in terms of this equation of motion. Basically, we have mainly described the stochastic process in terms of the Langevin dynamics. Okay, so where we have described everything in terms of the particle, and also we have summarized that one in a general form. So this stochastic process actually you can apply in any process, any stochastic process, which is not limited only to a physical system like this movement of Brownian particle in a fluid, not like that. So that is one way of description. So here another way of thinking that this instead of consider, basically we are talking about this stochastic process. So that means actually we have to describe everything in terms of these moments and in terms of this distribution function. In that way, you have to give a solution of a solution of a stochastic process. So the next step, actually, we can imagine that so instead of solving this kind of dynamical stochastic differential equation, can we actually convert this sort of equation by a evolution of the probability distribution function? Okay, so this kind of equation actually can we convert to a evolution of this probability distribution function? The evolution of probability distribution function, that is the question. Yeah, you can do, and that particular equation is known as this Fokker-Planck equation. Okay, how to get that one? So you know that we know that this distribution function f of at is there, and all the particles, just consider that there are some particles and these particles are actually they are following such type of equation, which is a Langevin equation, where this ft is equal to 0 and this correlation is actually delta function correlated. So you know that the distribution of that particle, so they are actually following a particular type of distribution. So we don't know what is the distribution. We are going to solve that one, and at least we want to write a differential equation where this evolution of this distribution function is there. So this, since all the particles are already in that system, so that means what? That this integrate over all the space of this distribution function always be 1. Okay, so that is kind of a normalization condition you can imagine, but it is basically, it gives you another intuitive idea that the system is actually conjugate. This distribution is actually conjugate. So always it is actually integration. If you do this integration, always you'll be getting the 1. So now, if this one is actually, if this relation holds, it means that there is a flux balance equation. Okay, so it's kind of a continuity equation. If such conservation law holds, it means that there is a continuity equation. So that is the argument I am giving. You can prove that one, and basically the physics student already know that one. So ultimately, it gives you a kind of a Liouville type equation. Okay, so I'm not going into the details of that one, and so basically I'm saying that they're just giving the argument that if the distribution function holds such type of conservation law, so it always gives, if it is there is a possibility to get a continuity equation, and this continuity equation actually it is like that. Okay, so this continuity equation is like that. So in that equation, actually, if you take a look, that there is del A del T, so that function, that thing is actually already there, and we can actually include that you can include this Langevin equation into that model, and ultimately you can get that one. Okay, and now, so there is a lengthy algebra to convert from this equation to that one. I'm not going into the details. So, but you can imagine that just take an argument that if we take the noise average of this equation, ultimately you can actually land it to this particular equation, and which is known as the Fokker-Planck equation. The steps are like that. So we have started with this Langevin equation. So the probability is conserved. So there is a conservation law like this kind of thing. And if it holds, so then always there is a continuity equation like this kind of continuity equation. And we have substituted this equation into that equation. Ultimately, if we take the noise average, finally we will be getting the Fokker-Planck equation. This is the steps. These are the steps. Okay, so you see that in most of the books actually you will find that always it starts with this distribution function is actually written not like that the average of that probability distribution function, but in Fokker-Planck equation always it is actually the average of the distribution function. Just keep in mind, it is not just only the distribution function, it is the average of the distribution function, and finally you will be getting such type of relation. Okay, so if it is like that, so we can actually take an illustration, take an example and illustrate how this distribution function actually, how this Fokker-Planck equation works. So start with the Langevin equation. We can take this kind of Langevin equation, and where we have ignored that the inertial term. So inertial term, this term, this m d2x dt square, this term actually we have ignored that one. So this is your stochastic differential equation is this one, and if you include this equation into the original Fokker-Planck equation, and you can recognize that this Fokker-Planck equation for this case it will be taking this kind of form, and it is known as the Smoluchowski's equation. Okay, where this diffusion coefficient is related by this kt by zeta. Okay, that one. So in the compact form, actually, you can write in this way, and basically, ultimately, this one is your this Smoluchowski equation. One important thing that I just want to mention here, this regarding this Smoluchowski equation, because it is a very simplest model where this kind of driven diffusion is happening. So if you take a look carefully, so this equation is a kind of a diffusion type equation, but there is the involvement of this potential. So it is a kind of you can solve, suppose you are going to solve a problem where the diffusion over a barrier is happening, such type of phenomenon is happening. So then actually you can model that kind of system by this kind of Smoluchowski's equation, where this potential is actually involved, where you can imagine that is a kind of a barrier is happening and diffusion is happening over the barrier. That one important thing that I also want to mention related to that particular equation, because not always true that one. So that is basically you can solve this equation by some trick. So the idea is actually this is a differential equation, partial differential equation, and you know, so that somehow this is kind of operator. Okay, so this is kind of an operator. And this operator can be if we can take the adjoint of that operator, and if it is a self adjoint, so then this particular equation you can actually convert to a such type of adjoint equation. And if it is if you can convert that kind of self adjoint equation, so then you can actually use the Sturm-Liouville theorem, and ultimately you can actually solve this equation in terms of this eigenvalue eigenvector. Okay, so that is the simplest way of solving this kind of equation, but this Sturm-Liouville theorem will not work for everywhere. Okay, so so basically that's why this is particularly one trick it is involved, where this FEQ, this F we can replace by this root over of FEQ by into G. So this kind of conversion is there. So FEQ actually some of you may be familiar with this one. So FEQ, that is basically the equilibrium distribution, and which is actually this one, this FEQ, which is basically the e to the power of minus beta h by q, where this h is the Hamiltonian and q is the partition function, and h actually is, you can write that the kinetic energy plus potential energy, where this p square by 2m plus ux, that one. Okay, so I'm considering everything in one dimension, that one. So if we consider that one, so this term, so this square root of this FEQ, so this potential energy function will be coming. Ultimately, it will transform and it will enter this e to the power this ux function into that equation. If you substitute into there, and finally you will be getting this kind of equation. This is a self-adjoint equation, and ultimately, if some of the physics student can actually recognize this is kind of a very much similar to the Schrodinger equation. Okay. So you can actually solve this equation. Yeah, ultimately it is an eigenvalue problem. So you can actually solve this equation in terms of this eigenvalue, eigenvector, and solution actually you can write. But this particular technique is not useful for every case. Okay, so this is a kind of a special case where you can plot. This is one of the important problems. You can model variety of systems by this kind of diffusion over a barrier in that way. Okay, so that's why this particular problem is very important in that context. So we will work on, we will actually, we will use this kind of problem with this model for further in the context of this rate, how to find the rate of a particular reactions, like that kind of thing. Okay. So to do that, first we need to get an idea about the first passage time. Okay, so we are mainly interested about the how to calculate the rate of reaction, like that kind of thing. Okay, so in that context, actually, we need to first know about the first passage time. So first passage time, what is that one? So suppose this, you have a dynamical variable like this AT and of a set of variables. So AT is a kind of vector. Okay, and they are following a Langevin equation. They are following a Langevin equation, and the initial point. So Langevin equation, whenever you are solving, you need to supply initial conditions. So this A0 starts. So this initial point is A0 that starts from somewhere in a volume element, like this kind of volume element, and where the V is the volume element, I'm saying, and the A0 is the initial condition somewhere in this volume element, and del V, that is the boundary. Okay, that one. So surface. So this first passage time actually is the first time that point, basically those points are actually crossing this kind of barrier or the boundary. So first time they are crossing that boundary, so that is the first passage time. And mean first passage time means actually the average of that time. So that will be the mean first passage time that we are going to calculate. So as I told you that these variables, they are following a Langevin equation. And since they are following a Langevin equation, so ultimately they will be following the Fokker-Planck equation also. So this kind of equation, because it is actually derived from that Langevin equation. So ultimately they will also follow that, the Fokker-Planck equation, and this Fokker-Planck equation actually they will follow like that. So this is the Fokker-Planck equation for this kind of arbitrary case, and here I have discarded that the average of that probability, rather than the average of that F, I've written in that way, that the del P del this in terms of basically denoted by this only capital P, that one. So need to solve this equation. And if we solve this equation, then you will be getting a probability distribution function, and that distribution function will help you to find that kind of first passage time. That is the idea. So this is the initial value problem. So you need to actually consider a initial we need to give a initial conditions, and also you need to give a boundary condition, because it is a initial value, and also the boundary condition also required here in the space part. So the initial condition is actually, I'm saying that all the variables or all the points, they are concentrated at some point in this volume element, and that is basically we can describe by a delta function like that. And on boundary, since basically there is no particle at the up beyond that boundary, so that's why on boundary actually we can say that this probability of that variables on the boundary is actually 0, that one. So once we give that kind of prescription, so then the formal solution of this differential equation, this partial differential equation, actually will be looking like that one. So it's PAT equal to e to the power of TD delta A minus A0, that one. Okay. So now the question is actually how many such type of points are actually crossing that barrier, crossing that boundary, that one. So you just take a look that we are going to calculate that how many points are there in that boundary. Those are not left yet. So if you are going to calculate that one, so that will be ST that I'm going to define in that way. So ST, that is, those are the number of points, and if you integrate it over the all space, so that will be that the PAT multiplied by this D, and taking the integral over all the space, that will be the number of points those are present at time t. Those are not left from that boundary. So now we are a little bit precise here. So here we are going to calculate that the difference, this ST minus ST plus delta T, that is the number of initial points that have not left before time, that have left during the time interval, means during the time interval dt, and following that basically dt following the t, and therefore determines the distribution of first passage time like that. So what I'm trying to say, that the ST minus ST plus delta T, so that is the difference. So that basically those are the points. ST is the number of points, and ST minus ST plus delta T, those are the number of points. Those are not left after dt time. Okay, so those are the number of points, those are not left. So if we know those kind of numbers, and we can actually calculate kind of a distribution, and those distribution function we can give a kind of a distribution function by this kind of a symbol like this rho. So if we know this rho t function somehow, or we don't know, it doesn't matter, so we can actually denote in that way. And this total, the number of particles, those are not left, so that will be kind of a rho t multiplied by dt. So that will then again this kind of this quantity also with the number of particles or number of variables, those are not left beyond that boundary, that one. So we can give a we can write a quantitative relation for this rho t. And this rho t with an initial condition a0, which is nothing but the minus of del s del t. From this relation actually we can write. So now we are going to calculate the mean first passage time. So mean first passage time is the first moment of t. So very simple. So we know, if we know this distribution function in that way, so then this mean means actually the integral 0 to t dt tau. Tau is that variable that we are going to calculate the mean of that tau variable, multiplied by this distribution function, that one, and this one. So this, now we can actually, we know that what is rho. Rho actually, if we substitute it there, so ultimately we will be getting that the d tau st. And if we take the part integration, if we do the integration by parts and take the limit t tending to infinity, because we want to apply this boundary condition. So if we take the limit, ultimately we will be landing to this particular equation, this d integral of 0 to infinity d2s dt s t a0. This one. This is the relation. So there is an indirect way of solving this kind of this mean first passage time also. So what is that one? So you can actually, if we know this dt st a0, so we know that what is the solution of that one, because that is basically the st a0, which is nothing but the integral of dA pa t, that one. So this PAT, which we know that what is the formal solution of this distribution function, so that is basically the exponential, this delta function, exponential delta function, this kind of function. So if we rearrange it a little bit, so ultimately you can actually write this equation in that form, and you see that if we take the integration over a, and basically this delta function drops one integral, and ultimately you will be landing to this particular relation, this 0 to infinity dt e to the power of t dagger 1, okay, that one. So this t dagger is nothing but the, what is this one? That is the adjoint operator. Okay, so d is the this operator, Fokker-Planck operator, basically this one. This quantity is the dp. So this is, and d dagger, so that is the adjoint operator. So adjoint of the d, so that is basically the d dagger. So we can write it in that way, and finally we can actually we can land to that kind of particular. So this particular relation is actually, it looks like very simple relation. So d dagger tau a, which is nothing but the, which is basically related by this -1. It is a, this is the basic relation for this, for calculating the first passage time. But already I have mentioned that this adjoint calculation of this d dagger for any system is not easy to find, and even if you can find that one, so then even the solution of that, even the adjoint of equation or the Fokker-Planck equation is equally difficult to solve. Okay, so it is not easy to solve. For Smoluchowski equation, actually it is easy to solve, because we can easily find that the adjoint, and the equation actually takes this kind of a self-adjoint form, and ultimately we can solve it in that way, this eigenvector eigenvalue problem. That is the thing. So then how to calculate this mean first passage time? So we have got a relation. So this d dagger tau a, that is basically the -1. This is the mean first passage time. By this relation, actually you can calculate this mean first passage time, where this tau equal to 0 on del v, means on the surface. So this particular relation actually we can apply for this Smoluchowski's equation. So we can calculate what is the mean first passage time for crossing that a particle over a barrier. So that time scale actually we can calculate. So there is a potential, and the particle is actually moving over the barrier, and how long will it take? So that time actually we can calculate from that relation. So that's why the simplest model actually gives you that kind of idea. So the Smoluchowski equation actually you can write what its self, this adjoint equation is like that, and that is basically from the, if you solve this equation, then you can actually get this tau x. Okay. So we are considering that these particles are actually moving along the x direction, starting some position on the x direction, and that is basically a Brownian particle. And we are imposing this boundary, this absorbing boundary basically. So this boundary at B, and we assume that there is a reflecting barrier at A. So basically, so this is the space where you are imposing that boundary at B, and which is basically, so absorbing boundary idea is like that. So if the particle actually goes there, see it will not return. Okay, so that is the idea of this absorbing boundary, and we'll see in the next example also we'll find that this idea again. So idea is actually we need to solve this particular equation, and we need to place that kind of absorbing boundary in the particular where we are actually from where actually we are going to calculate this mean first passage time. So this as I told you that there is a kind of a potential well, and where all the particles are actually at the potential minima, and all the particles are there. So that's why this is the A location, and first time actually we can integrate up to x, and we can get this kind of relation. So then again we can do another integration or up to that absorbing boundary, this B. So then you will be getting this particular relation. So ultimately this whole problem boiled down to this particular integral calculation. So if you calculate this integral, so you can get an idea that how much time is required to cross that particle for over that barrier. So that time scale actually you can get that from this relation. So we can get the time scale of that crossing, and if we take the inverse of that time scale, so then you can get the rate of that crossing. Okay, so that is a critical thing also in many cases. Actually this kind of calculation is actually very important. So we'll see, based on this kind of particular example, this Smoluchowski equation, we will find that how to calculate the rate of that equation. Okay, that is the thing. So any question from there, how to calculate, how to place this absorbing boundary, how to calculate this tau x from there? So any question from there? Any idea? Okay. Okay, so yeah. So again, I'm saying that yeah. So this is a more kind of a more physically actually we have described that how the potential actually looks like, and how to calculate this tau x, this mean first passage time, and we are going to apply the same thing for a real system. Real system means actually here we are considering a particular problem which is known as the Kramer's problem, and you can imagine that this is a bistable type potential is there, and you can actually, this potential wells are actually described by that way. So this type of potential actually you can imagine that this is a kind of a rearrangement. Means suppose kind of a basically from chemistry point of view I can say that suppose some isomerization is happening for a molecule. So this isomerization is a kind of a rearrangement. Rearrangement is happening in that molecule, and this is a kind of a dissociation. Means some chemical reactions are happening. Means if the molecule actually, if the particle actually cross that barrier, so there is no return at all. But if in this case actually in this bistable potential actually if it crosses, so this particular particle will be there. But if sufficient perturbation if you supply, so then they again cross that barrier. So there is a possibility, but in this case actually there is no possibility. So this is a kind of a, you can imagine this is a kind of a rearrangement, and this is a kind of a phenomena related to this dissociation, that one. So this, in this case actually, so this is a kind of a physical problem, physico-chemical problem you can imagine, and ultimately you can actually solve that what is the rate of that particular reaction. That thing actually you can calculate. So this rate of this particular reaction you can calculate from that what is called this the way actually we have calculated in the previous slide, that one, this first passage time. So anyway, we have to place that absorbing boundary where basically these particles are actually moving there, and if it moves there, so then they will absorb, so there is no return. So we have to place that boundary in properly, and if we place them properly, so then ultimately you can actually calculate the mean fast passage time. So in this case, so these are the potential wells. Actually, just consider this A diagram, and the B diagram is a little bit easier. So I'm not done that calculation here, but this diagram is actually easy to comprehend. So we know that what is the fast passage time for the, we are considering this thing actually in terms of the Smoluchowski equation, that one, and we are how to calculate that one. So this formula, this equation already we have developed, and this is the equation, and we need to place that absorbing boundary condition properly. So if we place that absorbing boundary condition properly, so then we can actually calculate this tau x in that way. So this is the particular equation, and if we are imagining that the absorbing boundary actually we are putting at that barrier, so that at x max we are actually putting that barrier, so that is the absorbing boundary location, and there is a repelling potential, and that is basically at x equal to infinite. Okay, so there is a repelling potential that is actually at the infinite. So now the thing is, what is that? So you need to do this integral properly. So you need to place that basically is minus infinity to plus y, so that will be kind of a molecule. You can imagine that from minus infinity place to y, some certain location. Actually, you need to do this integral, and after that, actually you need to take the integral from x to absorbing boundary. So ultimately, it will be giving you that the mean fast passage time of the basically mean fast passage time of crossing that particles over the barrier, that one. And once we get that tau x, so then we can actually take the reciprocal of that tau x, so that will be giving you the rate of that reaction. Okay, so for both of the cases, actually you can do, but I'm saying that this tau x actually will be giving you the time, this mean fast passage time, that if you take the reciprocal of that one, so that will be giving you the rate of that reaction. One important thing just I want to mention, that this whole experiment or whole theory that we have discussed here, so that is basically we are considering that this barrier is sufficiently high, and or you can imagine that the thermal energy is sufficiently low, means KT energy is very low, or the barrier is high. So under the condition, actually this particular relation actually holds. Okay, so just keep in mind that one. So how to calculate that one? So as I told you that this absorbing boundary and this barrier is actually placed on the barrier, and these are the these potential minimums are there. So we can actually do the potential, we can expand this potential around the minima and maxima. And so if we do this expansion, this first order term will be 0, because we are ultimately there, the minimum or maximum, this first order terms will be 0, and the second order term, so basically this constant, this will be the frequency of that one, and if we put it there into that equation, so then this first integral will be giving you this type of relation. Okay, this is basically the simple algebra. Ultimately, you need to do this potential Taylor expansion, and ultimately the first order term will be 0, because you are considering that the minimum of the potential, so that will be 0, and this constant term will be the frequency of that one, and this term will be also be there. So then what will be that? So you need to do the integral, this first integral actually you are going to do, and this integral actually if you do, so ultimately you will be landing to this particular relation. The second thing, you are going to do the same thing for on the absorbing boundary, because the second integral is associated with this absorbing boundary, basically at the barrier. So that thing also, if you do this Taylor expansion on that barrier, it is maximum. So again, the first order term will be going to be 0, and again actually you do the same calculation on that barrier, and do the same, do this integral, do this integration, and finally you will be landing to this kind of relation. So why this half appears? Because if the molecule or the particle is on the barrier, so it can actually go in this side or in that side. So these are the equal probability. So that's why this half probability actually we need to multiply, and finally we will be getting this type of relation. So finally, this tau x actually is a kind of the difference between the potential maxima and minima, the potential barrier, basically that difference is there, and tau x is actually related to that one. And this particular relation is very important. Why? This is because actually it relates with the this classical theory of this rate equation. So Arrhenius law, actually you can imagine. So this Arrhenius type of equation, it is there because it is the difference between this potential barrier. Ultimately, it is giving you such type of equation. So what we have found that so even for a simple problem like that kind of thing, actually we have seen that the existing empirical theories also validate by that microscopic theory of this particle. And another important thing is actually that we have seen that this friction, this is the friction, and this friction is there, and you can actually control the rate of the reaction by introducing the friction constant. Means friction constant means actually you can change the medium, and ultimately the rate of the reaction you can control. The rate of reaction you can increase or decrease depending on what will be the friction constant. Friction constant means ultimately you need to change the viscosity of the medium. So that also related by this Stokes-Einstein relation. Just keep in mind that one. Okay. Any question from there? So how to place that absorbing boundary, how to do this kind of expansion, whatever it is. Any question from there? Okay. Okay. So now, so whatever we have done, so based on this Langevin dynamics, we have arrived to a evolution of this probability distribution function, that is basically the Fokker Planck. So you can imagine that the Brownian motion in the probability of space, and we have taken few simple example like this Smoluchowski's equation, and also we have solved some of the problem like this, how to calculate the rate of reactions, or such or how to calculate the mean fast passage time. So for a complex system, this calculation of this mean fast passage time is not easy, because the way actually I have shown, so we have taken a very simple model, so that's why it is easy to calculate analytically. But most of the complex problems, actually you cannot solve it. Most of the time actually you need to do this kind of numerical way of doing this calculation, and finally you can calculate if you use the logics, the way actually we have presented here, so that the use of the same logic, actually you can calculate this mean fast passage time and also the rate of that reaction. Okay, that kind of thing. So next step, actually, we are going to describe this whole Brownian motion in the probability of space in another way of describing this this evolution of this probability, that is the master equation. Okay, this master equation is a typical probability equation. All of we, at least to some extent, actually we know. And recall that in the Brownian motion, the Einstein theory, actually whatever we have discussed, that is this evolution of this density is like that. So as I already mentioned, that the rho of xt, so this is the density of the particle at t plus tau. This is the current time. What is the location of this particle, position of this particle, and if it experiences delta amount of push, and if we multiply it with this distribution function and take the integral over there, so ultimately we'll be getting this kind of relation. So we are going to this integral equation we are going to use to describe this kind of this probability balance equation, which is basically this master equation. So this equation relates the distribution function of the Brownian particle at x and at time t plus tau to that particle at previous position x plus delta and at an earlier time tau. So this is the earlier time, t is the earlier time, where the location of the particle was that x plus delta. We are considering everything in the one dimension, and the current time is the t plus tau, and the location of the particle is actually x. Okay, so we can imagine that this y, we are introducing another variable. This x plus delta is, we are denoting by this y, and if we denote by that way, so dy equal to d delta, and we can also write that the phi delta equal to basically the transition from the y to x. Just take a look that one, phi delta. We are writing that from the previous to current, that kind of transition is happening. So this previous position to current position, actually we are writing by that way. So this y to x, and the pxt we are writing by a new variable. So that is basically rho xt we are writing by a new variable pxt. So we can write in that way. So just put this kind of variables in this above expression. So ultimately what you are getting, that the p of xt plus tau and phi delta, that is nothing but the phi of y tending to y to x, that transition, multiplied by this p of yt dy, that one. Okay, so this one actually we can again actually we can rearrange a little bit. So we can expand this left hand side in that way. So ultimately we can get that one, this pxt plus tau dpxt dt, that one the first term. Second term, actually second and higher order term we are neglecting because this tau is very, very small, we can imagine. So ultimately this we can move this pxt from left hand side to right hand side. Finally we'll be getting this kind of expression. So we knew another fact, that is this phi of xt x to y. So that kind of transition, that is basically the current location to the previous location, that kind of, so that is the kind of opposite of that phi delta. So that's why this phi of minus delta, and we know the integral of that one. So because phi delta is a symmetric one, so ultimately this integral of that one at always be 1. Okay, that one. So here we can actually replace that in the previous slide, actually what I've written that this tau is there. So we are going to write that this transition, this phi y to x or x to y or x to y, that one, this transition divided by this tau is denoted by this capital W, this one. So if we write in that way, so then, and if we substitute this fact, so this one factor actually we are multiplying there. So ultimately we can arrive this type of probability balance equation, this dpxt dt del pxt del t integral of this transition probability from y to x multiplied by this probability at time t, and x to y, that is multiplied by the probability at x, okay, at time t, that one. So we can actually, this is the kind of a probability balance equation, and it is known as the master equation, and W is the probability jump for unit time. And once we write this kind of continuous version of this master equation, we can immediately write the discrete version of that master equation. So just we can write the discrete version of this master equation is like that. This integral we can write in the discrete form in that way, where this Wmn are the transition probability in the discrete sense, which you can imagine that the gain of m state due to transition from other all n state because of the summation, and this one is the loss due to transition from the m to all other n states. So all other n states actually very much important because of the summation. Actually, we are going to consider that in that way. So one important relation is related in physics or in physical science. That is basically if the probability at equilibrium, this dp dt at equilibrium, that will be 0, and ultimately this relates like that, and this summation, this relation also implies that the WNMPN EQ equal to the WMNPM EQ. So that is, this particular relation is, some of you are familiar, I think. So that is called the principle of detail balance. So it is kind of a microscopic reversibility or the microscopic description of the equilibrium. So that is actually given by this relation, and this is a very, very powerful relation. This detailed balance actually, if the system is equilibrium, so that means actually the detailed balance equation always holds there. Okay, just keep in mind that one. So in our description, because we are mainly modeling this kind of chemical process or the population biology modeling, actually those kind of thing actually we do. So in that sense, actually we are not that much interested about this kind of continuous version of this master equation, because whenever we are describing some of the physical chemical process or some in the population biology, actually some processes are actually going on. So those are kind of a discrete process, and these discrete processes actually we can describe in the framework of this discrete version of this master equation. So that is actually quite easy to implement, and we will show in some of the by few of the two examples. Okay, and one important thing that I just want to mention that this is basically the probability balance equation, and that actually and it is a very general equation, whatever you can imagine. Okay, that. So now, yes. Any question from there? Any question? Okay. So just we are going to execute this particular relation, this equation, this master equation. So so just take a very simple example, one-dimensional random walk. So you can imagine that so these are the lattice points, and these points are actually moving, or the particle is actually moving over the lattice points like that one, and we can actually describe that this movement of this particle in terms of this how many steps it has moved from this left to right by NL, and how many steps it has moved from right to left, that is basically the R, like that kind of thing. So these are the two variables we have introduced. So left to right, right to left, that kind of. So this is a kind of a discrete type of description how this movement of these particles are happening. Okay. So you know that the NL, so we have introduced this variable. So this is the NL is the total number of jumps from left to right, and NR is the total number of jump from right to left, like that kind of thing. So current state, actually, if we know this NL and NR, this current state actually is basically the difference between this NL and NR. So if we just take this picture carefully, that so these are the lattice points and they are moving in that. So these are, the arrow means actually it is changing their states. Okay. So this is basically the how many steps it has moved from left to right. So that is the NR equal to 1. And in that case, actually the NL, so there is no movement of this NL leftward movement. So that is basically NL equal to 0. If you consider these two arrows together, so then the NR will be 2 and NL will be 0. If you consider this one is actually this one together, so that means actually, so this whole path together, so that means actually the NR equal to 2, NL equal to 1. So that's the complete path for this kind of description. So if we have such type of movement, this is kind of a random walk, and if we write down the master equation for this case, so then the master equation actually looks like that one. So this is basically the forward rate equation for from left to right. So if we define the rate constant like this, from left to right KR and right to left by this KL in that way. So then actually this basically we know the rates, and ultimately we can write this master equation in that way. This is you see that this is an infinite dimensional problem. So this, you can imagine that this lattice points can be infinite number of points. Ultimately, if you are going to describe this process, this kind of work, you have to describe by this kind of equation infinite number of such type of equation, and which is a very difficult job to do. So in other way, actually you can do, this is a jump, this kind of jump actually we can write in terms of the generating function method. And basically why we can use basically this equation is actually in the form of the linear form. So that's why we can use this kind of generating function method. So if we use this generating function method, this is the generating function, and ultimately if you manipulate this function into this expression, finally we'll be getting a simple first order differential type equation, and solution of the differential equation will be like that. So this infinite dimensional problem actually boils down to a one-dimensional problem, like that kind of thing you can imagine. So you see, now the thing is actually we are not interested about this G, we are interested about this PNLR, because this is the grand probability distribution function. Whatever property or whatever moments we are going to calculate, anyway we have to calculate this PNLNR. So that probability. So if we somehow calculate that one, so then obviously we can actually calculate all of the statistical properties. So we can imagine, we can say, so basically we have already got this G function, and what we are going to do, we are going to expand it in terms of this with respect to R. Okay, so if we expand it, so finally we'll be getting such type of relation. So just exponential function we have expanded. That's all. So ultimately you have see this kind of relation you have got, and now we are going to compare this relation with your original definition of this generating function. So just take a look this one. these are the original definition of the. So this quantity multiplied by this SL to the power NL, SR to the power NR. So that one is already there in this case. So the left hand, this part is actually basically this PNL NR, this part. So if you compare them with the previous expressions, ultimately you will be getting this kind of probability function. Okay, so this probability function, and you see that it follows a Poisson distribution. It is a kind of a independent Poisson, two independent Poisson process, and ultimately it's a product of these two Poisson processes. You can imagine that. So this distribution function, actually, if we know anyway, actually we can calculate the any type of moments, okay, and which is very important in the context of this analysis of a stochastic, if we are going to analyze a stochastic process. Okay, so this generating function method actually has a useful property like this kind of, you can calculate the moments, all the moments by that way. So just taking the differentiation with respect to that SL, SR variable, ultimately if you take the derivative one time, so then you will be getting the first moment, so that is the average, and if you take the second, so then you will be getting the variance, and you can also calculate any other moments, whatever you want, based on this kind of probability distribution function. So this distribution function actually looks like this one, and the moments actually, if you take the derivative of that one, so ultimately you'll be getting the moments will be looking like that one. It means that this generating function methods has some certain advantage, right? Although it is we have applied for a simple problem, but if you somehow model your system in this way, so where this kind of this jump processor happening, you can actually formulate your problem by this kind of master equation way, and ultimately you can use this generating function method. And the beauty of this method is like that the generating function method actually reduces infinite number of coupled equation to a finite number of dynamical equation at an expense of new continuous auxiliary variable. This SL and SR are the auxiliary variables. And the whole expression relatively simple, involving only a strategic placement of auxiliary variables within the ordinary equation of motion. So that ordinary equation of motion, actually you will be getting that kind of thing. So the method also provides the probability distribution and the statistical moments for the occurrence under investigation, and possible to track multiple types of events within a single generating function equation of motion. Each type is associated with unique auxiliary variables. Okay, so that type of thing actually it is there. So this is a kind of a hypothetical model. You can imagine that the kind of a one-dimensional random walk on lattice, but it is easy to comprehend. That's why we have taken such type of example. But you can mimic such type of model with many other actually real system. That also you can imagine, and such type of thing actually we have described one particular example. So so this particular, actually you can imagine that the chemical kinetics actually I have written, but you can imagine that this kind of model also be applicable for a population biology also. So here we are going to describe this whole process by some master equation and want to get some solution of that one. Okay, so how to write that equation, and can we actually convert this master equation to a Fokker-Planck equations to get kind of a continuous probability distribution function of this type of process, that kind of thing. Because you know this particular reaction is like that. This A plus B goes to A, that one. So it is a kind of a react with B, ultimately it is giving you the 2A. So it is a kind of a autocatalytic reaction. So basically the conversion of this reactant also be in the right hand side, so like that kind of thing. So here we are introducing the number of particles in that way. So this M is the number of particles A, and N is the number of particles of B, and I'm saying that this is a conserved system, so M plus N equal to N. So whenever you are going to describe what time, yeah, so just this is the last thing. I'm just trying to finish this one. So M plus N equal to N. Okay, so this is the conservation law, and if you are going to state of that system by a vector like this m and n. These two numbers actually are sufficient to describe the state of that reaction. So if we somehow manage to count that m and n, and then we can actually completely specify that what is the state of that system, at least for this case. So this prescription, this reaction, actually we can describe in that manner. So kind of a elementary steps. You can imagine that this reaction actually happens in a two-step manner. This A plus B to A and A plus A to A plus B. Okay, so that one. So, and if we are going to, so how these jump processes are happening, how are we going to formulate that particular thing, this jump process in this case? So it is basically, suppose in the earlier time, so this t minus tau time, if we start that this reaction, this A reaction, from a molecule actually starts from this m minus 1, and once it actually goes to this t time, so then this basically it reaches to this particular state, this MNF state. So this is the t minus tau is the earlier time. What was that state? So this is that particular state, and at current time, what is that state? So we are looking for how such type of jumps are happening. So in t minus tau, for this case, if we just take a look that if we start from this m minus 1, because it produces one A in the right hand side, that means the net in the net reaction, actually always, if some reaction, this particular reaction happens, it always gives you 1 unit of m molecule, like that kind of thing. So that's why if we start from m minus 1, that is the previous state, and if it elapse this tau time, so ultimately it will reach to that particular mn state at time t. Similarly, for the backward reaction, A plus A to A plus B, so if we just take a look this particular reaction, so here actually this A molecule is actually reducing. The number of A molecules is reducing, whereas the B is the number of B molecules is actually increasing. So it means that the m plus n, so it is reducing. That means actually if you start from m plus n, and n actually if you start from n minus 1, so then it can actually it can reach to that mn state at time t. So these are the two jump processes for this particular reaction. For the simple reaction, actually we can imagine. So this is a kind of a this jump process actually we can write in the master equation form, where this mn are the variables, and in this case actually we can write this master equation in this form. So just this is the probability, as I told you, that you have to imagine that the jump from this state to that state, that is the gain state, and the mn to the disappearing state, so that is the loss state. So for the both cases, actually you need to write that the gain state and the loss state, and ultimately you will be getting the 4 terms in this master equation, that one. So since there is a conservation law, so this conservation, so you can reduce the number of variables. Ultimately, you can express everything in terms of this m variables. So that thing actually you can write in this manner. So this is the master equation, and ultimately your master equation is like that. So now the thing is actually we can write this master equation in a more compact form with the help of the shift operator. So this thing actually we can, if we just shift operator, actually it defines like that. So if we operate this operator on this PM, so then it is actually increasing 1 unit of m molecule, and similarly this backward shift operator, actually it gives you that the 1 unit of m molecule it is reducing, that kind of thing is there. So if we include that one, so into that expression, so then you can write this master equation in a more compact form in this way. And now we are going to convert this equation. This is the kind of a discrete version of that chemical process that is happening, and we are going to convert this equation to a Fokker Planck, which is basically the continuous version of this jump processes. So what we are going to do, we are changing some variables. So we are going to convert this number of molecules to density or concentration, and the probability, this grand probability, this probability function, instead of writing this probability, we are going to write that the probability density function, and ultimately we can get a Fokker Planck equation if we expand in terms of this volume. So so basically what we have done, so we have done this scalar expansion of this quantity, and just use this kind of variable that I have written here, and in the all form we have done this kind of expansion, and finally we can write this shift operator is just like this kind of form. and the backward shift operator will be just like this kind of form. So basically we have a clear cut, basically we have got the relation of this, what is the functional form of this shift operator and the backward shift operator by that way, and then we can substitute it there, and ultimately you can get a equation that is basically the Fokker-Planck equation. This is a continuous version of this equation. So basically I'm saying that this equation also you can solve, and ultimately this equation is very much useful to find the potential, this stochastic potential of this kind of jump processes. Even any arbitrary system actually you can find. So you can easily identify that the event that is a completely unusual type of system, like a chemical reaction that is happening, but you can write, you can easily recognize this is the kind of a Langevin part, and that is basically the kind of a that is basically the deterministic part I'm saying, not the Langevin part. This is the deterministic part, and this is basically the noise part, which we can compare with the original version, the way actually we have derived this Fokker-Planck equation. So immediately you can recognize this is the deterministic part and this is the stochastic part from this Fokker-Planck equation, and you can easily actually do this kind of simulation with the help of some algorithm. You can get this kind of potential with the help of this kind of equation, or you can actually do this kind of simulation, some other algorithm like this Gillespie simulation we will discuss in the next lecture. So one important difference that I just want to give stress, that in the Langevin formalism actually whatever noise actually we have included, so that is a kind of external noise. Okay, we have included some noise into the system, that is a kind of extrinsic noise or external noise. But in this case, the inherent stochasticity is associated with when the particular reactions are happening. Okay, so this is a kind of intrinsic stochasticity or inherent stochasticity. It is within the system, that is actually related to the when a particular reaction is happening. We don't know, that is actually a stochastic event. Okay, so just keep in mind that one. So this type of jump process, this type of chemical reaction, or the model related to this population biology, those things actually mostly related to this kind of, if you describe these processes by this kind of elementary processes, so that is kind of you are describing in the form of this intrinsic noise. And whereas the Langevin dynamics, or the kind of a Brownian motion, the Brown basically in that way actually it is basically the extrinsic noise. Just keep in mind that one. So in the next lecture, what I will be doing, this is a simple case. So that's why we have written down the right set of equation. We can actually expand, ultimately we can get the Fokker-Planck. Even that equation can be solved for this particular case. But the problem is actually, even for a complex case, like suppose a systems biology related problem, where the many molecules are actually going, and many reactions are happening, or even a population biology, many processes are actually going on in that system. So you can write the master equation, but the solution of the master equation is not easy. Okay, so you have to know a good strategy how to simulate such type of system. So that thing actually we will be discussing in the next lecture. So any question? Any question?